Without further ado, it is my great pleasure today to introduce Mr. Trevor Ablett, who will be giving his DDS seminar. Trevor came to us originally from McMaster with 2 degrees under his belt, I believe, 2 undergrad degrees, and has done a whole bunch of wonderful things in the lab related to RL, ML, deep learning, etc., which he's going to tell you about. I'll also point out that Trevor spent some time in Zagreb with our colleagues there in Croatia, and did a nice stint at Samsung AI Research as well in Montreal, where he produced some really nice work that was recently presented at in a couple of conferences and journals, and we're delighted to hear him summarize his work. So without further ado, sir, I turn it over to you. And yeah, if I drop out for any reason, I'll be right back. I'm just my Wi-Fi should hold steady. But sir, over to you whenever you're ready. Clap in advance.
Second here. Okay. Hi, friends, colleagues, family, and fellow researchers. Thank you so much for joining me today. My name is Trevor Ablett, and I'm here to talk about my PhD thesis on addressing distribution shift in robotic imitation learning. So human motion is incredible. The way that these babies, let me just get that off the screen. Hold on. Sorry about that. The way these babies and toddlers move through the world, manipulating arbitrary objects, easily resolving and learning from failures, is beyond the state of the art of our robotic systems. And by contrast, most of the way manipulators are used in industry is completely unlike human motion. Highly accurate robotic arms complete repetitive tasks with ease, but they're only useful for certain tasks, such as welding or moving car frames. And many people may not realize that we still haven't been able to automate many aspects of even high capacity products, such as cars, because the dexterity of human motion is very hard to duplicate. So how can we get more human-like motion from our robots? Here's a 10-year-old video of some highlights from a 2015 DARPA-funded challenge. The goal was to complete a series of tasks, including requiring a human-like form, such as turning a valve, opening some doors, climbing some steps. And some of them did better than this, but even when they didn't fall, the successful robots took far, far longer than a human would. Here's a video from this year from Figure AI, and the results appear to be much improved, but these robots are still very robotic. And I know I just showed this video on the last slide, but he's my son, so I can't stop watching it, and it's my talk, so I'm just going to show it anyways. But there's a point. His motion is completely unlike even the state-of-the-art manipulation that we see from the Figure video. So for unstructured tasks requiring a high level of dexterity, humans do very well, and robots generally still do quite poorly. This is Moravec's paradox. What's easy for machines is hard for humans, and crucially, what's hard for machines is easy for humans. We had millions of years to evolve perception, planning, control, sensing, and actuators, and our ability to understand how these things work is still quite low. Here's a video of a human doing a task that's relatively easy for us that we'd like robots to be able to do. But I can say with confidence that completing this task with this level of fidelity is, again, beyond what our current robots are capable of. Why is this so hard? We need state estimation where we decide what sensors to use, such as vision or touch. We attempt to determine where our bodies are, where the things we care about are, and how to model these things. We also need planning, where we produce a motion plan for how to move our multi-jointed system to complete tasks, have to consider possible collisions and contact, and how we will determine whether a trajectory is optimal, efficient, or safe. And we need control, where we must actually expend the energy to accomplish the plan, deciding on what actuators to use and how to accommodate on-the-fly changes to the environment. Roboticists try to stitch the state-of-the-art of all of these fields together, and none of them are solved individually. So since programming robots is so difficult, is there another way? Consider these 3 example robots from the last 15 years. Even as far back as 2010, and actually even further back, we've been able to teleoperate robots far more competently than we're able to program them. Can we use this teleoperated data to make robots learn to act like humans? What do I mean by learning from data? This is what the field of machine learning deals with. Instead of trying to program rules and logic by hand, we use clever algorithms and data to allow the system to figure out the correct outputs on its own. And this approach has seen remarkable success in language, computer vision, game playing, biology, even in robotics. What would machine learning applied to manipulation look like? Consider a door opening task as an example. We could treat our system states or observations, S or O, as, for example, raw camera or depth images, other raw sensors or robot positions. We can make our policy pi any learnable function, such as a linear mapping, a convolutional neural network, a transformer, and the learned actions could be joint positions, torques, velocities, 3D positions, velocities, or gripper open and close commands. Sometimes these approaches are called end-to-end, meaning that we only provide the outputs or the ends and allow the model to learn the decisions. So given that we can teleoperate the robot, we can use imitation learning, or IL, to learn one of these end-to-end policies. In its most common form, known as behavioral cloning, or BC, IL allows us to learn policies by directly mapping expert observations to expert actions. We collect a set of observations and corresponding actions from an expert, run the observations through our agent to get policy actions, get the error or loss, and iteratively update our policy actions to minimize the difference between the expert and the policy. This process is known in machine learning as training the policy. And BC is easy to apply because it's identical to supervised learning, which has very robust tools. The only difference is that behavioral cloning is supervised learning, but applied to sequential decision making. So can we solve manipulation and possibly even robotics with behavioral cloning? Let's see if we can produce a quick answer to that question. In behavioral cloning, we collect an expert data set to train on, or a distribution of data. For example, we might have a set of trajectories of a robot completing a door opening task, shown as the separate dotted lines here. We then train a policy on this data. And what happens in practice is that the robot starts executing and gradually makes small errors. The effect of each of these small errors compounds until the robot reaches a state that's no longer within the expert distribution. And since there's no labeled data here, the robot doesn't know what to do and it fails. This is called distribution shift. This effect is inevitable when training with behavioral cloning. Supervised learning as well, but it's exacerbated in sequential decision-making settings like robotics due to the effect of those compounding errors. Each of these videos shows agents that were trained with behavioral cloning, and each one of them fails because of this distribution shift. So in this presentation, I'm going to go through my research efforts to address this problem. This slide will also show the venues they were published in. I'll start with approaches that stick with completely offline learning, as I described in the introduction, but we modify the procedure for collecting data. First, I'll show an approach where we handle multi-view data by deliberately widening the expert distribution. Next, I'll show an approach where we modify individual expert trajectories via a force matching procedure to better match the test distribution. I'll then outline an approach that serves as a halfway point between offline and online approaches, where we predict when the policy will fail and allow the expert to provide corrective data. Next, I show approaches based on online learning. The first one breaks up expert demonstrations into main tasks and auxiliary tasks, improving exploration. And finally, I expand this to a harder regime where we only have access to expert examples without full trajectory demonstrations. These approaches can be thought of as being on a continuum where the first approach has the highest burden to the expert and the last approach has the lowest. Okay, let's dive into multi-view demonstrations. So much research in end-to-end policies for manipulation focuses on the case where a robot is mounted in a fixed position and tasks are completed from this single position. However, a more realistic case for human-like manipulation occurs when we have a mobile base, where we can't expect the base to pull up to an object or cabinet with the exact same pose every time. In this work, we refer to these two cases as fixed base and multi-view. We were interested in answering the following questions. Can end-to-end policies handle base location and viewpoint changes as would be expected during mobile manipulation? And secondly, if they couldn't handle this, would multi-view data allow it? To answer these questions, we collected human expert data sets of multi-view and fixed-base data and trained on them with behavioral cloning. After training, the hope would be that the multi-view policies would have improved performance over policies with fixed-base views. We would also hope to be able to partially explain this discrepancy by observing more consistent feature labeling between the viewpoints. We developed a scheme for autonomously generating base poses such that the task-relevant objects were in view of the sensor and within the reachable workspace of the arm. All that's necessary for this is reasonable calibration between the base and onboard sensor, a desired workspace center point, a desired max and min angle to set the base to, and rough localization of the base between episodes, for which we found wheel odometry was sufficient. As shown in the diagram on the left, we generated poses along an arc around the workspace center, in this case directly in front of the door, and we add a small amount of random noise to increase robustness in the policy. None of this extra information is required at test time since we only use it to generate the poses. The video on the right shows what our expert data collection process looks like on our real platform. You can see the end effector or the gripper tracking the expert's movement, and between episodes, you can see the base changing from one pose to another autonomously. We tested our method in the 7 tasks shown on this slide. For each, between episodes, we vary the initial block or cylinder pose, the initial gripper pose, and of course the base pose. In the fixed base versions, we still randomize object positions, but not the base positions. Each of these videos is shown at 3 times real time. We only required 15 to 30 minutes of actual robot interaction time per task for the collection. We tested multi-view and fixed base policies in both the multi-view and fixed base settings to see how important the multi-view data really is. The architecture we use for policies is a convolutional neural network with a fully connected network head. Notably, the CNN finishes with an attention-like mechanism called spatial softmax that extracts 2D feature points before concatenating them with other numerical state information and passing that through the fully connected network. We train these policies with just mean squared error and no other auxiliary loss functions. Here we compare multi-view policies with fixed base policies on our 7 tasks in both the multi-view and the fixed base regimes. Success rate is on the y-axis and the number of demonstrations on the x. The largest benefit of multi-view policies shows up in environments where we cannot randomize task-related objects' initial poses. For example, we can randomize both block positions in StackSim. Conversely, in the door tasks, for example, we cannot randomize the shelf pose, meaning the benefit of multi-view data is much more pronounced. Also, multi-view policies are either not or are only slightly penalized in this fixed-base tasks, despite having little or no data from the specific fixed-base view. Altogether, these results indicate that multi-view policies are effectively able to generalize between views, and that fixed-base policies often fail in the multi-view setting. And just a second. So I just have to restart PowerPoint because I have too many videos and it does this every now and then. There we go. Okay. Here we show our door real task from 4 different angles, along with the corresponding sensor data used for each run. Take note especially of the large difference between the handle positions of the top left and bottom right sensor data, as well as the difference between the base poses. And consider how different the arm trajectory would have to be to accommodate this. It may not look like much, but the fixed base policy completely fails due to these changes. Specifically, comparing the top left and bottom right poses, the base is 50 centimeters apart with a 30 to 40 degree change in the viewing. We examine the spatial softmax features learned by both fixed base policies and multi-view policies in multi-view tasks. We started by looking at our fixed base policy, pi-f. At the top, we have 5 different angles or episodes of our door sim task where we show the highest activating gripper feature. There's a high degree of spread for this feature, indicating that it doesn't consistently correspond to a single part of the scene. Here we show the same, but for the highest activating feature on the door. And again, there's a lot of spread across the door. Now we show the top 3 features on both the door and the gripper. Now we switch to the multi-view policy. Note how the point is relatively consistently indicating the same side part of the gripper, displaying less spread and more consistency than the fixed policy features. On the door, the multi-view policy has learned to consistently associate this feature with the same top part of the door handle. And here are the top 3 features on the door and the gripper for the multi-view policy. Finally, here's a comparison between the feature distributions from the fixed base policy and the multi-view policy, where the difference in spread becomes much clearer. The multi-view policy has learned to consistently label the same parts of scenes with the same features, regardless of viewpoint. And remember, we didn't train the policy to do this. This just came out. Okay, let's move on to force match demonstrations. So when humans manipulate an articulated object, like a door or a drawer, their fingers use normal and shear forces. They respond to dense tactile feedback in their skin. They move quickly. They can manipulate small and challenging knobs, and they don't require a firm, stable grasp. Specifically, we can use an approach based on pressing and pulling, allowing the handle to roll and slip against our finger, compared with the more common robotic approach requiring a firm grasp and then a very large arm motion. For one robotic example, see the video from the work that I just showed, where the robot motion had to be very slow, it didn't leverage much shear force, and the handle had to be really large to allow the robot to hook in. To get robots to be more human-like, we need dense tactile feedback, visual feedback for reaching small targets, and complex control policies that can respond to that feedback. In this work, we use a visual tactile sensor for dense tactile feedback. The sensor is partially transparent to allow robust reaching of small targets, and we use imitation learning via kinesthetic teaching for learning complex control policies from that feedback. Let's take a moment to talk about teleoperation, kinesthetic teaching, and forces. So much imitation learning work, including my last work, uses teleoperation for collecting demonstrations, but one limitation is you don't get any true contact feedback from doing that. So in this work, because we didn't have this contact feedback, the arm's own safety mechanism kept protective stopping the arm and forcing us to do demonstrations very, very slowly. This is obviously not ideal. So with kinesthetic teaching, the demonstrator does receive some contact feedback, but it only records the robot positions and not the actual control actions when you use kinesthetic teaching. And the operator can also corrupt the sensor data with their shadow, for example. And this can be partially resolved by resetting the robot in the environment and then doing a replay of the demonstration. But even if you have replays, because you're not recording forces, you can end up with poor data or even replay failures like this video. Okay, let's take a moment to also introduce this see through your skin visual tactile sensor. An STS sensor has a small, inexpensive camera and a deformable gel-based material on the surface that's loosely meant to resemble human skin. The novelty of the STS sensor is that the top layer is translucent, and the controllable lighting allows us to have multiple modes. Specifically, we have a visual mode with the lights off, allowing one to view non-contact visual info, such as the knob as we're reaching to it, and a tactile mode with the lights on, allowing one to view dense contact info as the skin and the painted on dots deform, such as while the skin rolls and slips against the knob. Okay, now I can introduce the full system. As part of our data collection process, we collect a raw demonstration with kinesthetic teaching. And throughout this demonstration, we use an STS sensor in tactile mode to measure unscaled force based on marker displacement. We generate a new set of modified poses as input to the controller that not only recreate the kinesthetic teaching poses from 1, but the forces from 2. And finally, we run a force match replay of the original trajectory, simultaneously acquiring an expert label for switching the STS sensor mode from visual to tactile. We do this n times, for however many task demonstrations we want, and then we train our policy on the force match replays with behavioral cloning, where our policy inputs are STS data, optionally an eye and hand wrist camera, and relative pose information. And our outputs are the motion and the STS mode. So our contributions for this work are the force matching method, a method for using imitation learning to switch the STS mode, and a study of the value of the STS data as a policy input, compared with the more common approach of simply using an eye and hand wrist cam. Here we show demonstrations and force matched replays of each of our 4 tasks. We collected 20 raw kinesthetic teaching demonstrations of each. An initial reaching component between the robot and the handle or knob is required, as shown on the right. An absolute pose is not provided in the observation, and we randomize the initial pose between the handle and the knob. These choices are meant to simulate the same mobile manipulator scenario from the previous work, where a mobile manipulator will pull up to a cabinet but not have reliable, repeatable, known base pose relative to the door. The initial reach requirement is meant to simulate the scenario that a simpler reaching or planning policy can get the end effector close to the object of interest, but not complete the much more challenging task of actually opening or closing the door. This video shows a single run of the actual autonomously running policy for each of our 4 tasks, including force matching, learn mode switching, and all 3 sensing modalities. The performance results on the right show that including force matching, mode switching, and the STS as input significantly improves performance. Here's a set of replay failures when force matching is excluded. Notice that because they're replays and not policies, the arm continues through the task trajectory even after it's failed. It's making my son very upset. Here we show a comparison of STS data with mode switching. And I think, oh, there we go. Of STS data with mode switching, STS with visual only, and STS with tactile only for the glass knob close task. During the reach, tactile only data is quite poor, whereas the opposite is clear during contact. And here's examples of failures with visual only and tactile only policies. The wrist camera is shown only as a reference, and it's not actually used in these policies. Notice that the visual only policies effectively reach, but often make poor initial contact or do not maintain contact. And the tactile only policies are often not able to reach at all, since without having a wrist camera or an STS in visual mode, they can't even see the knob or the handle. Okay, since we're about halfway, we're just going to tune into Wesley Bowie TikTok for 20 seconds, just to give everyone a breather. For all the people online who don't get to actually see my son, there he is. All right, so let's move on to failure predictions with interventions. So as I mentioned at the start of this talk, both previously presented methods are based on behavioral cloning, which is purely offline learning, meaning that we collect a data set and we train once. Here I'm showing diagrams of performance changes with increasing data from my own multi-view work, as well as two other more recent papers, either based on BC or including BC as a baseline. If we focus on a representative part of each diagram, we see a classic plateau curve as the number of demonstrations increases. The lessons from these works regarding BC are that we need exponentially more demonstrations to get corresponding gains in performance. There's no way to know how many demonstrations we need until we get acceptable performance. And there's no way to predict when these systems, which are not performing at a 100% success rate, will fail. So in other words, the first two presented methods can help mitigate distribution shift, but not resolve it. The widely known approach to resolving distribution shift in offline IL is dataset aggregation, or DAGGER. After training pi on your expert data DE, you run it to get policy data dpi. You relabel the states in dpi with corresponding expert actions, discarding the original state or original actions. You add these new pairs to DE, and then you retrain, and you do this iteratively. This procedure generates a policy that's as good as the expert, but it has two major problems. First, running this policy will result in many failures. And second, labeling these states from dpi offline is typically impossible for most systems that we care about. A reasonable alternative is to allow an expert to take control of a running policy when they think it'll fail, bringing the policy back into a desirable state. The new expert data is then added to the expert data set, and otherwise we exactly follow the procedure from DAGGER. On the right, I have two videos of some preliminary tests I did using this approach in a car racing domain. The video on top shows the results of training behavioral cloning on 5 laps of training data. The video on the bottom shows the results of adding a few laps of intervention data. So clearly it's not an optimal policy. I wouldn't want either of these cars driving me around, but the bottom one is a huge improvement from the top one, which fails almost immediately. But unfortunately, this puts a high burden on the expert to be diligent. So can we predict policy failures? So to address failure prediction, we introduce a method called FIRE, failure identification to reduce expert burden in intervention-based learning. We start with a policy learned via behavior cloning. We then roll out the policy, adding data to the policy dataset dpi. Concurrent to this process, we run a failure predictor that uses data from both dpi and DE to attempt to identify states and actions that don't resemble the expert. If no failure is predicted, execution continues. If there is a failure predicted, execution stops and an expert is notified. If the expert agrees with the prediction, they provide intervention data to return the robot to expert-like states, and the data is appended to DE. If the expert disagrees with the prediction, execution continues. Finally, we use false negative and false positive predictions to adjust the threshold for predicting failures. We trained a deep discriminator to predict failures. The architecture is the same as the architecture for the policy, which is actually the same as the architecture for the first work, but with a different head. We use this because deep classifiers have been shown to be successful in generative adversarial networks for identifying subtle differences between real and fake data, even in the high dimensional image space. A deep discriminator also trains using both expert and non-expert data, which meant no data was wasted. And at the time, a lot of methods only used the expert data set. We then retrained this deep discriminator after each episode. The approach based on raw discriminator values worked okay, but it was flawed. Here we plotted the average per time step discriminator values for both successful and failed episodes of our pick and place XY task. Discriminator values for both successful and failed episodes tend to correlate with the episode time step. Notice that to have a single effective threshold, we would have to both choose a threshold that was above the highest discriminator value for the failed episode, and as a result, delay making the prediction until quite late in the episode, which may not necessarily be helpful. It might be better if we could use these statistics to make predictions based on the optimal boundary at all time steps. For example, we should be able to use the gap between successful and failed episodes from time step 30 to 60 to make better predictions. And other tasks showed a similar problem and also required delayed discriminator predictions. Here we've plotted the raw discriminator values for an entire successful episode from pick and insert on the left, compared with the corresponding probabilities of failure using discriminant analysis on the right. You can see that a single threshold discriminator would be nearly worthless for this whole episode. The highest average discriminator failure value is above most successful episodes, and the lowest average success value is below most failed. But after discriminant analysis, we're able to use a single threshold, correctly predicting success despite sections of the episode with lower discriminator values. Okay, we ultimately tested our method in 5 tasks, the 3 that I mentioned, as well as 2 more difficult and longer horizon tasks with multi-view based positions, like the work that I showed earlier in this presentation. Here we show the performance results of FIRE compared with behavioral cloning with increasing amounts of data on the easier tasks. While FIRE clearly improves performance based on the raw amount of data, this can be slightly misleading. And in fact, in later work, we found that if you spent the same amount of time just collecting more demonstrations in BC as you did actually running FIRE, you ended up with similar performance. So to mitigate this for these harder tasks, we instead compare the raw robot execution time, meaning that on more difficult tasks, FIRE clearly provides significant benefit over BC. The receiver operating characteristic curves show that our method based on discriminant analysis clearly most accurately predicted failures compared with discriminator only, which is labeled as beta here, as well as a state-of-the-art method based on ensembles. Here we show an example of a robot completing the stack 2 task, along with the plot showing whether a failure will be predicted. Okay, I just have to restart it again. 1 second. When the failure is predicted after the green block is dropped, the human briefly takes over control and returns control to the agent. One more failure is correctly predicted when the red block isn't released, and the human again takes over control and adds corrective data. Conversely, in this episode from Pick and Insert, the prediction never reaches the failure threshold, and the episode is completed successfully. Here we show an example of the robot completing the stack 2 task. Sorry. One of the benefits of this approach is that it allows the policy to learn to recover from errors, whereas the BC policy never recovers once it makes a mistake. Okay, let's move on to auxiliary task demonstrations, which is our first work based on fully online. So to recap, we collect a set of expert data and train a policy on it, but the policy suffers from distribution shift when it sees data it's never seen before. We just described an approach to resolve this issue based on interventions, attempting to predict when failures would occur to reduce the burden, but this method is ultimately still quite expensive in terms of human effort. Wouldn't it be nice if we could just have the agent explore autonomously, finding its own path back in distribution after making errors? To achieve autonomous exploration, let's introduce a new concept, reinforcement learning. In contrast to imitation learning, our task is now defined by a reward, and we learn a policy online by continuously looping between executing the policy, getting reward from the environment, and modifying the policy to maximize the reward. In inverse RL, the reward maximization and policy execution parts of the RL loop stay the same. However, we now learn a reward function using our expert dataset DE, which outputs high values for data resembling the expert and low ones for non-expert, like the mechanism we used for predicting failures. Now our policy autonomously learns to match the expert distribution at test time. A well-known example of inverse RL was used for learning autonomous helicopter stunts, which was a part of Peter Abeel's PhD thesis. And many people may know, but both Peter Abeel and Andrew Ng are now quite famous researchers in the world of AI. In our attempt to apply these algorithms to manipulation tasks, we found a problem. The agent can ultimately learn a locally maximal policy that only partially matches the expert and then stops improving. This can also be thought of as a deceptive reward, where the agent is rewarded for partially matching the expert distribution without actually completing the task. Specifically in this case, the agent receives partial reward for the sections of the trajectory that match the expert. Poor exploration and deceptive rewards can co-occur, ultimately resulting in suboptimal policies. In practice, this deceptive reward manifested as the policies shown here, where learning would stop and settle in these local optimums that didn't complete the task or only completed it partially. We can describe an approach to resolving this problem by discussing forms of feedback in reinforcement learning. Consider this hammering task, where a robot hand has to grasp a hammer and hammer the nail. As originally formulated, this task had a fairly complex reward function with many terms that likely had to be tuned to get reasonable performance. As discussed, in inverse reinforcement learning, we replace this reward function with demonstrations of the task being completed, but it can lead to deceptive rewards. In this case, since the correct final state may only have the nail driven in, the robot may learn to do nothing because the hand and the hammer in the initial state match the final state. Previous work, called scheduled auxiliary control, introduced hierarchical reinforcement learning, where multiple policies learn separate, simpler rewards with the purpose of improving exploration and manipulation tasks. In our work, called learning from guided play, we use the same learning framework, but we instead use expert data for auxiliary tasks. Expert data can potentially be easier to acquire or more informative than handcrafted rewards. Here I'll describe the building blocks of LFGP in more detail. First, we again show the inverse reinforcement learning loop. In reality, this is implemented as adversarial imitation learning, where the reward is learned as a discriminator. LFGP is a hierarchical approach that adds semantically meaningful auxiliary tasks, such as reach, lift, and release for this stacking task. LFGP uses a scheduler for high-level selection of low-level control policies. The scheduler can be learned, random, or selected from predefined sets. LFGP learns a set of discriminators from multiple expert data sets and a single policy buffer, learns a set of critics, and then at test time, only the main task is used, since the scheduler was only meant to improve exploration. To refer back to our motivating door opening example, we could start with having full demonstrations of completing the door opening task. We would then also collect separate reaching only demonstrations, which would be one of our auxiliary tasks, since these could not be exploited by the policy and would force it to explore near the door handle. And then in the final work, which I'll present shortly, we do in fact use reach for a door opening task. So for this work, our main tasks were stack, unstacking, and then stacking, bringing, and inserting. And then our auxiliary tasks, which are common to all of these four main tasks, were release, grasp, reach, lift, and move object. These were our primary results for LFGP, where we showed dramatically improved performance over both single task inverse reinforcement learning and behavioral cloning. LFGP was also able to share expert data between auxiliary tasks, further emphasizing its expert data efficiency. And I'll spend more time on the results in the follow-up work. Here's a video comparing the learning progression between LFGP and single task AIL. Notice that even at only 200,000 steps, LFGP has learned reasonable policies for its auxiliary tasks and performs far more diverse exploration of the environment. Once we reach 800,000 steps, LFGP has learned to stack, while DAC has just learned a highly suboptimal policy. Okay, we're almost there. Finally, I'll discuss a follow-up to LFGP, where we exclusively use auxiliary task examples. Returning to our earlier discussion regarding forms of feedback, rewards in RL are often broken up into dense and sparse. Dense rewards have many terms corresponding to a full trajectory, and sparse rewards, on the other hand, only reward the final task being completed. This leads to a less biased reward, but it generally makes for a much harder exploration problem. The issue was first identified in the 50s by psychologist B.F. Skinner, who used dense rewards to teach dogs how to open wastebaskets. And as a dog owner, this is still more or less how you have to train dogs, but ours can't open a wastebasket. A domain that receives less attention is sparse expert rewards, where we're only given a set of expert examples of a completed task. This is sometimes called example-based control, or EBC. Final states, unlike full trajectories, cannot be suboptimal, and in most cases are much easier to collect. Wouldn't it be nice if we could just show the dog the open wastebasket and say, figure out how to open this? But unfortunately, this approach can be very sample inefficient and is even more susceptible to the deceptive reward problem that I previously mentioned. So these videos all show policies learned via state-of-the-art example-based control, and they're all stuck in local optimals. So our main experimental question is it possible to learn policies efficiently given only example states of completed tasks? There are two related ways we can motivate our follow-up to LFGP. LFGP requires full trajectories, which can be suboptimal or difficult to acquire, and this motivates the use of EBC, but EBC can suffer more than inverse reinforcement learning from deceptive rewards, resulting in inefficient learning. So the solution is to apply learning from guided play to example-based control, and we call this auxiliary control from examples, or ACE. This does improve exploration dramatically, but it also results in highly overestimated value functions that break learning. Take a look at this example of the overestimation. Here, a partially learned agent learns Q values for arbitrary motion that are higher than Q values for successful states. For the time being, it's enough to say that Q values are an estimate of how much future reward a state and action pair will earn. To prevent this scenario, our goal is to keep Q values less than or equal to Q values of expert successful states, since nothing should be higher than those. We can enforce our goal as a quadratic penalty whenever Q estimates go above this max value. Now our policy will correctly learn to avoid unsuccessful states. Here we show our setup for our real-world experiments. The images on the right show samples from the initial state distribution, as well as samples of the experts' example states used for training our real-world and door and drawer tasks. And notice how much easier these are to collect than demonstrations of full trajectories, where I collected each of these sets of states within seconds. Note that these aren't stuttering videos, but this is rather a slideshow of the static successful examples we used for training. We completed tasks in 4 environments, with example tasks shown in the bottom left, and we actually did 21 tasks in total for this work. For all 21 tasks, we used either just reach and grasp or reach, grasp, lift, and release as the set of auxiliary tasks, showing how easy it is to define useful tasks. We considered 3 single task inverse reinforcement learning baselines. One was actually designed for the example-based setting. And then we also included an exploration novelty bonus, which was R&D, showing that providing bias on how to explore was necessary, rather than rewarding any exploration at all. VPace, which is our method, improves performance in all tasks, but value penalization makes a bigger difference in the harder SimPanda tasks. And we hypothesize it's because they're longer horizon and have a larger observation space. And crucially, VP never harms performance. These videos show exploratory policies after 40 minutes of training. The left columns for VPace show task switching in real time, while the right columns show time lapses over 4 minutes total. SQIL, the highest performing baseline, fails to make progress on this task. Here are the same comparisons at 2 hours, where VPace has started to open the door. And here they are at a little over 3 hours, where VPace is now successfully, consistently opens the door. This is the final performance of the main tasks without executing any auxiliary task, showing that the main task now subsumes the auxiliary tasks. Okay, so what can we conclude from my work? A lot of people ask me if robotics will have a GPT moment, alluding to the idea that if we just provide enough teleoperated robotics data, we'll eventually have a robot that can just achieve arbitrary tasks. The GPT comparison is made because the power of ChatGPT caught everyone off guard, even in the AI and robotics community, in late 2022. And they did it by basically scaling up the amount of data that they had. But I'd argue that robotics cannot be solved by simply scaling data up, because no matter how much data you have, distribution shift will be inevitable. And in fact, we know that this approach doesn't work for LLMs or video generation models either, because they hallucinate. And even after being trained on, in the case of language, all of the text data in the history of the world. And to make matters worse, robotics data is actually much, much harder to deal with than language. But if we're careful about what data we use, we continually query humans, and we figure out how to allow robots to self-explore, then I think there is hope for end-to-end learned methods for robotics and for manipulation. If you're interested in learning more about anything you've seen in my presentation, please ask in a few minutes, or email me, or have a look at any of these corresponding project pages. You can find links to the full published papers as well as more videos. And finally, each of these works have code and data to reproduce the results. And finally, I must acknowledge a few people before I end this presentation. The experience of completing my PhD, which actually isn't complete yet, but almost, was often extraordinarily difficult. And it wouldn't have been possible without the people and the animals that you see here. In addition to many, many more, but I can't make this slide be 10 minutes. I want to thank Jonathan Kelly, my supervisor, for always being willing to let me work on whatever harebrained ideas I wanted to, and continuing to provide guidance throughout. I want to thank everyone from the STARS Lab. I couldn't have asked for a friendlier and more supportive group of people to work with. And finally, and most importantly, I have to thank my wonderful partner, Christina, who's here today, who's been a source of inspiration throughout, and without whom I would have probably given up years ago. And that's it. Thank you so much for listening, and I'd be delighted to answer questions.
Outstanding. Okay, thank you. Let's thank our thank our Trevor. I'll clap. Trevor, do you want to take questions from the audience there first?
Sure. I can only see like a subset, so if you want to handle that, John, that would be really helpful.
Yep, maybe do the local first, and then I'll check the chat.
Okay.
I see one hand up. Vincenzo has his hand up. Yeah.
All right. We got a question from someone in the audience here. Yeah. So for people online, the question was about how sensing changes and sensors change and improve. How do we deal with that and incorporate that in our models and in general in robotics? Which is a really good question that I think people in the field are also constantly dealing with this. I know for myself, throughout my time as a PhD student, we've changed sensors. We've also changed robotics over time because they get better especially now, even in very short amounts of time. So I don't think there is one answer. I think one of the popular answers right now is that a lot of companies are just trying to scale up data as much as possible. And then the hope is that if you add in data from all kinds of different places, different sensors, and put it together into a big model and somehow figure out how to use that big model, it'll just benefit it. I'm not so sure that we're going to see the rewards from that right away. But I think that that's like an open question, that we kind of just have to do the best we can with the best sensor we have at the time. Some companies also take the approach of saying, like Tesla, for example, they're like, well, we don't want to put LiDARs on our cars. We're only going to use visual sensors, which has pros and cons. But one of the pros is that visual sensors already are quite good. It's unlikely that we're going to get cameras that are that much more high fidelity than they already are, whereas LiDARs will probably keep improving. And so you can use data from maybe 5 years ago, whereas with LiDARs, maybe you can't. But I think it's a really good question that doesn't have a good answer. Got another question from the audience. Thank you. Right. So first of all, John, I don't know if you heard, Christina and Wesley are waiting for their honorary PhD. And second of all,
we can do that. We can do that.
Great. You're recording it, so it's on record. So
I mean, he is imitation learning. He's basically the prime. He is imitation learning at the moment. This is great. It's great. Yeah.
Yeah.
Sold.
Yeah. He opened a drawer this morning, so we're saying he's pretty much halfway as good as the robots already. The question was, in our results, we found that VPace actually ended up outperforming LFGP. So using the examples actually outperformed using full trajectories, which she had some privileged information to know that, because I actually didn't show those results here. But the question was, would there ever be a time where you would want to use full trajectories instead of examples? And I think it would be if there were tasks where it would be very hard to divide some very complicated motion into specific examples, then it might make more sense to have those complex motions be trajectories, because you'll learn more efficiently. And also, if you're doing something that requires really high velocity movements, using examples where you're not actually moving might not be the most appropriate way to use data. Yep, another question in here. Thank you. Okay, the question is, what advice do I have to students starting a PhD? Because I always ask that question. My advice is do it in less time than I did it. No, I think that the most succinct thing is look for opportunities to collaborate and to get feedback, potentially harsh feedback on your ideas as quickly as possible, because I'm not sure that I did that. I think I spent a lot of time in my early years going down paths without really knowing what I was doing, which is fine. That's going to happen in your PhD. But if you don't have someone else to kind of check you and be like, hey, like maybe we should do this or maybe we should do that, you end up just like losing a lot of time. And then you can get into this situation where you're like, oh, now I need to publish, but I haven't done enough work. And it's a very hard thing to do and an easy thing to say and hard to enact. But I think like just be open to that feedback and be looking for it. Be actively looking for that feedback as much as possible. It's not always automatic that you can find collaboration. Every time I found collaboration, my work ended up much better for it. Yep, another question. Thank you. Great question. The question is, as a dad now, what do I hope for the future of robotics in the world, and what's my vision for what the future could and should look like, I think. And I am very excited about all, like, I think we're at like a really kind of big inflection point for a lot of AI methods and robotics, where I think for a couple of decades we were making very, very incremental progress. And then in the last couple of years, things have really started to take off. And my hope is that people continue to use these things to apply them to like, I guess not war. Yeah, so like any application that actually is kind of what robotics was originally supposed to be for the dull, the dirty, and the dangerous, that's where we really want to see robots. I mean, it would be great to have them in our homes, being able to help us out. People talk about aging populations and like that obviously those are kind of like the dream applications. And I mean, I hope that I can contribute to getting us there. Yeah, I think that as long as we continue to prioritize, I think I believe in humanity, and I'm an optimistic person, and I think that people will ultimately use these things for good, and it will be hard in the short term, but I think things will be exciting as Wesley grows up. There's just so much going on right now, and things are always there's always new things to learn and new things to see. So. Okay. Yeah, another question in person. Yeah, so the question is about using robots to teach robots. There is work on doing this kind of thing, particularly in simulation, where so sometimes people refer to that as like self-play. And this isn't exactly the same as robots, but for example, you might have heard of Go or AlphaGo. This is a result from reinforcement learning 5, 6, 7 years ago. There was like a Netflix documentary on it. That was trained in part by self-play, by having two agents playing against each other and ultimately improving by doing that. And I think that for doing that specifically with robotics, it's easy with games to frame them in kind of that like competitive way. To frame it in more of like a teaching way would be really interesting. The problem is robots are still pretty bad at a lot of things. But there's actually a number, we should talk about it more later, because there are a number of ways where robots are used in this way, where, for example, we might collect data with a robot that has privileged sensors, like we were talking about LiDARs and whatnot, and then train a robot that doesn't have those sensors to be able to have the same performance with simpler sensors. And that's actually a robot training a robot, basically. And there's some really, really cool work, and that's kind of like a subfield that's actually gaining a lot of traction now. Okay, I think that's it for in-person questions. Anything online?
Okay, folks online, would anyone like to ask a question? I saw one hand, but then it went down. Oh, Vincenzo. Vincenzo has a question.
Hello. Yes. Thank you for. Yeah, can I go with the question? Oh. Okay.
Yep. Sorry, go ahead.
So thank you, Trevor, for the presentation. That was actually really interesting. I mean, I'm not into manipulation much, but I tried to follow and was quite clear. So thank you. And so, but I have a questions because I mean, I've been seeing around, like all these vision, language, action models that I mean try to be really actually interesting under the point of view of like generalization, all this kind of stuff. But do you think that your methods, for example, can be somehow integrated into this kind of system, or they provide some kinds of guarantees that this super huge VLA don't?
Yeah, so sorry, the wonderful projector at UTIUS is a bit choppy, but I think I heard your question was, given like VLAs and the new very large VLA models, can I use my work and somehow integrate them into VLAs? Is that possible? Is that about right?
Yes, and how, I mean, yeah, also like how this compares to VLA, like how your works against VLA, what like the guarantees that you can have respect to, for example, VLAs.
Oh, sure. Yeah, okay. So that's something I didn't really address it in my presentation at all, but it's a great point because these VLA methods are starting to become really serious and a lot of companies are putting a lot of money into them. All of my methods that I presented here, apart from the last two kind of, are basically single task in the sense that they're meant to optimize performance on a single task. Whereas the whole idea with the VLA method and just for people who don't know, a VLA is a vision language action model where this is basically the approach I was talking about, where they try and use as much data from as many sources as possible, train a really large neural network on it, and then kind of hope that it's going to do really well on a variety of different tasks, possibly by fine-tuning it. And I think that is basically one way that you could directly integrate any of the methods that I have here. Is you could start with the pre-trained VLA and then fine-tune it using any of these methods, which I would suggest in general, not even necessarily with VLAs, but pre-training is almost always going to be better, especially when you're looking at single task, like applying things to single task. Pre-training and then fine-tuning is kind of the go-to. It's actually pretty hard, as it turns out, in many cases. Like, for example, my last two works, theoretically, you could pre-train them with behavior cloning and then use reinforcement learning to fine-tune them. But this is actually surprisingly difficult, and still a lot of companies, even if they're promising being able to do that, aren't necessarily able to do it with robotics data. And even people who know how to do that on like language data, for example, can make a ton of money right now because just the engineering effort involved with doing that is hard. So I think the answer is you could use these methods basically to fine-tune VLAs. You could also use the data generated from these methods as just another source of data in VLAs. But that it's almost like shockingly hard how hard it is to do the fine-tuning. Considering how the way it's promised as being like, oh, it's obvious you do imitation learning and then reinforcement learning, but like it's just so much harder than saying it. But yeah, it's something that I think people should be looking into.
Okay, thank you so much. Yeah, interesting. Thank you.
Okay, thank you. We have another question from a gentleman named Olivier. You may have met him at some point.
Cool. Yeah, thanks, John. Thanks, Trevor. That was an awesome presentation. And I hope the people in the audience can appreciate all the amount of work that went into having these hardware demos to your experiment. That's great. I had a kind of question that maybe built upon what Vincenzo was talking about. I was wondering, how do you see imitation learning scale beyond single tasks applications? Like, say you have 2 or 3 tasks. The bigger the overall task is, there's a greater chance of having greater distributional shifts, right? I assume it kind of blows up exponentially. So I was wondering, would you still use imitation learning in these settings, or would you take a different approach, like more pure reinforcement learning for tasks with longer horizons?
Yeah, that's a super good question, and something that I think about a lot. I think that using pure imitation learning for very long horizon tasks is almost certainly the wrong way to go in the short term. Some companies are working on it, like Physical Intelligence right now, for example, is working on doing things like this, and they're getting reasonable performance with like their kind of laundry folding tasks. But I would say for most tasks that are like, that if you fail, there's a lot more consequence, that right now, given where the methods are at, it's almost certainly the wrong way to go. So if you think about, like, for example, like Waymo, like Google's self-driving car company, we don't know exactly what they're doing under the hood, but almost certainly they're not running it through a large imitation learning model. They are using imitation learning. That I know, because I've had people in the same conference talks areas of me in the imitation learning section talk about it. But it would be, again, I don't know exactly what they're doing, but it would be, for example, like maybe you have like a 3-second maneuver of like a lane change or a right turn in the case of cars. And then for manipulation, and this is kind of how I try to choose my tasks, you might have like the actual like grasping and opening of the door, like some kind of 3-4 second task is the one policy. But then in between all of those things, like if you wanted to say, like, I want a robot to go from this room to this other room that's like 100 meters away and go through a few doors and then plug in itself to charge it, of course you should not use imitation learning to do that. It just, like, the distribution shift, as you said, would happen immediately, and it would be a crazy amount of data that you would have to collect to do that. And we also have really, really good tools for handling, planning, and some collision avoidance and a whole bunch of other things, where we should really only be, in my opinion, using imitation learning for things that are still very hard to program, which is, for that task, for example, the actual plugging in, that's still really hard. So that's why you even see in conferences, a lot of people are still doing insertion and plug-in tasks with imitation and reinforcement learning, because that's where we're still having trouble. So I think that's my answer, is that like the best we can do right now is mixing things together and trying to use both imitation and reinforcement learning for the parts that we still find hard.
Cool, thanks.
Okay, one more call for questions online. Anybody?